So, what is the universe really made of? I mean, what is everything actually made of? It's a question we've been asking for thousands of years. And the quest to answer it, well, it's not just some dry history of science. It's one of the greatest detective stories ever told. It's a story about following clues, chasing down false leads, and peeling back layer after layer of reality to get to the absolute heart of everything. So here's our game plan, our investigative roadmap, if you will. We're going to follow the trail from the very first ideas about elements all the way to the atom. Then we'll see what happens when scientists finally crack that atom open, and we'll try to make sense of the chaotic particle zoo they found inside to get to the ultimate building blocks of, well, everything. All right, so our story kicks off with the very first attempts to solve this mystery. And you got to remember, the only tools they had were their own two eyes and, pure logic. So the question was simple. What are the fundamental ingredients of the world we see around us? What's so fascinating here is the massive shift in thinking. For centuries, the answer seemed obvious. It was the stuff we could see and feel, right? Water, earth, air, fire. But science came along and revealed this whole hidden layer, showing that those things weren't fundamental at all. Nope, they were made of even more basic stuff, the chemical elements. This was the absolute first necessary step on our path. We had to realize that the world was basically written in a hidden alphabet. And that idea led us straight to our first prime suspect, the atom. A guy named John Dalton proposed that each element, like hydrogen or oxygen, was made of its own unique, unbreakable particle. It was an amazing theory that explained everything they knew at the time. For a lot of scientists back in the 19th century, that was it. Case closed. Matter is made of atoms. End of story. Or so they thought. But you know how these detective stories go. Just when the mystery seemed all wrapped up, these strange new clues started popping up. Clues that suggested our indivisible suspect was hiding some pretty big secrets. The case was about to get blown wide open. So picture this. At the end of the 19th century, this was the accepted image of an atom, just a tiny, solid, featureless ball. Think of it like a microscopic billiard ball. It was the smallest, most fundamental thing you could possibly get, period. The first piece of evidence that didn't fit came from a totally different area, the study of electricity. Scientists were messing around with these vacuum tubes, and they noticed these weird glowing rays. Now, if atoms were just solid little balls, where in the world was this mysterious energy coming from? It just didn't make sense. And boom, here's the breakthrough. J.J. Thomson proved that these cathode rays were actually streams of tiny negatively charged particles. He called them electrons. This was it, the first definitive hard proof that atoms were not indivisible. This was the key piece of evidence that absolutely had to be found before this investigation could go any deeper. Once the electron was discovered, it's like the floodgates just opened. A little while later, Ernest Rutherford finds this tiny, dense, positive core, the nucleus, and the proton inside it. And then finally, James Chadwick discovers the neutron, also hiding in the nucleus. In just 35 years, our picture of the atom went from a solid ball to this complex miniature solar system. It was an incredible period of discovery. Now, unlocking the secrets of the atom, well, this wasn't just some academic thing for the textbooks. Understanding its core, the nucleus, would unleash a power that was going to reshape human history in ways nobody could have possibly predicted. It all comes down to a process called nuclear fission. Scientists figured out that if you fired a neutron at a heavy atom, something like uranium, you could actually split its nucleus. And when it split, it didn't just break apart. It converted a teeny tiny bit of its mass into a truly massive amount of energy. And this shows exactly why it's so powerful. See, when that nucleus splits, it also releases more neutrons. And those neutrons, they go on to split other nuclei, which release even more neutrons, and on and on and on. It's a chain reaction, and the energy release just grows exponentially in a fraction of a second. It's mind-boggling. The consequences of this were, well, staggering. This single discovery led directly to the atomic bomb, for sure, but it also led to peaceful applications that totally define our modern world. Nuclear power gives electricity to millions. In medicine, radioactive isotopes are used to diagnose and treat cancers. And in research, things like carbon dating have completely revolutionized how we understand history and even the age of the Earth itself. Okay, so case closed for real this time, right? We've got protons, neutrons, and electrons, the whole set. But just as scientists were getting comfortable, new evidence started pouring in from high-energy experiments, revealing that this conspiracy went much, much deeper than anyone imagined. This was the beautiful, simple picture. A nucleus of protons and neutrons, with electrons orbiting around it. It explained chemistry, it explained radioactivity, it seemed to explain pretty much everything. But turns out it was just too simple. And then came the particle zoo. Using these powerful new particle accelerators to smash atoms together, physicists discovered this absolute flood of new exotic particles. We're talking muons, pions, lambdas, sigmas. It felt like every single experiment was revealing another one, until there were literally hundreds. The simple, elegant picture was just gone, replaced by total chaos. This wasn't just more information, it was a crisis. Was nature really this messy? And it turns out, this confusing stage was a necessary one. It forced a complete rethink of what fundamental even meant. But out of all the chaos of that particle zoo, a beautifully simple idea started to emerge. An idea that didn't just add more animals to the zoo, but explained what the zoo itself was actually made of. The final verdict was finally in. The answer, the elegant solution, was quarks. Proposed by Murray Gell-Mann and George Zweig, the idea was that those heavy particles like protons and neutrons, they weren't fundamental after all. They were actually combinations of even smaller, truly elementary particles called quarks. It was a radical idea. It suggested that all that messiness in the particle zoo was just a shadow of a much simpler reality hiding underneath. And here's the aha moment. Just look at how perfectly this works out. A proton is made of 2 up quarks and 1 down quark. You add up their weird fractional charges, and what do you get? A total charge of exactly +1. A neutron is 1 up quark and 2 down quarks, giving a total charge of 0. Suddenly, the chaos of the zoo made perfect sense. All those other exotic particles were just different combinations of a few types of quarks. This simple bit of math tamed the entire zoo. So when we look back on this entire journey, from fire and water all the way to the quark, a really profound idea starts to take shape. Was this winding path of discovery just a series of lucky accidents? Or was it something more? Inevitable? This right here is the core argument from our source. The path of discovery wasn't random at all. It was dictated by the very structure of nature itself. Think about it. We had to understand elements to even come up with the idea of atoms. We had to discover the atom before we could find the electron inside it. We had to find that messy particle zoo to realize we needed something simpler underneath it all, like quarks. Each discovery was the necessary key to unlock the very next door. And that leaves us with our really fascinating final thought. This journey of discovery, it's not over. So if the structure of the universe itself is laying out the path for us, what clues are sitting right in front of us today? What great mystery, like dark matter, dark energy, or quantum gravity, are we being guided, step by necessary step, to inevitably solve next?